So we're going to graph general rational functions. So in the rational functions we actually graphed last night, in this form, y equals p of x over q of x. P of x and q of x are either both linear or the top part may have been a constant like 3 or 2 or 1 or -7 and so forth. But tonight we're going to look at this assuming that p of x and q of x are not linear, as in not degree 1, and degree something else. For example, let's say we have y equals to x raised to some power divided by x raised to some other power, where m is the degree of the top, n is the degree of the bottom. So m is the degree of the numerator. M is the degree of the numerator, and n is the degree of the denominator. So let's get this clear. Lots of different things can happen. For one, if m is smaller than n, as in degree on top and degree on bottom, if m is smaller than n, then the horizontal asymptote is 0. So if m is smaller than n, then the horizontal asymptote is 0. If m equals n, as in degree on top is the same thing as degree on the bottom, then horizontal asymptote is you divide the leading coefficients. So if m equals n, then the horizontal asymptote is equal to the leading coefficient divided by leading coefficient, wherever that fraction is, whatever it reduces to. Just so you know, if I had a plus k on the end, you may actually see one like that, and n is equal to m, well, it would be dividing the leading coefficients, or whatever that is, plus k. So if you have a plus k on the end there that's not a part of the fraction, and you want to find the horizontal asymptote, and these two numbers are the same thing, they're equal to each other, like 6 and 6, well, then you figure out the leading coefficients divided by each other, plus that k that's on the end there. It's kind of nice to know. I'm going to erase that though, because that's kind of unusual, but just in case you ever do see that, that's what you do. And the last thing is, if m was greater than n, as in the degree on top is bigger than the degree on the bottom, different things happen. If it's greater than n by 1, you have a slant asymptote. If it's greater than n by 2, you have a quadratic asymptote. But if m is greater than n, there is no horizontal asymptote. No horizontal asymptote. But you do have other weird kind of asymptotes. You may have slant asymptotes, or end behavior asymptotes. End behavior asymptotes. End behavior asymptotes. Basically, what end behavior asymptotes are, the end behavior follows some kind of quadratic or cubic equation, and the slant asymptote is like a linear equation. Look at all those now. All right, so say the direction said graph the function y equals x squared plus 2 divided by x squared plus 1. Well, to get started, we need to find out vertical asymptotes and horizontal asymptotes, or any other asymptotes. It might be slant, or whatever else it may be. So in this case, our vertical asymptote we still find the same way. To find our vertical asymptote, we would set the denominator equal to 0. Squared plus 1 equals 0. However, from what you learned about factoring, you may recognize that x squared plus 1 really can't become 0. Because let's think about this. In order for that to become 0, I have to square a number that's the same thing as -1. Or for that, make that 0, has to be -1 plus 1. And you can't square a number and it'd be negative. So it may ring some bells that this is really impossible with real numbers. So you will have imaginary numbers. So when you subtract 1, you see x squared equals to -1. And bell should ring again. X squared can't be -1. So when I square root this, we get x equals to positive or negative I. In this case, no vertical asymptotes exist because you can't actually graph positive negative I on a real number line. So there are no vertical asymptotes. So since there are no vertical asymptotes, our domain is all real numbers, meaning that I can plug in any number I want for x and it still be true. There's no way of making the denominator 0, which is great. So there are none, meaning that this graph continues on every number there is for x. Now the horizontal asymptote, if you look at this, the degree on top is 2, the degree on the bottom is 2. Since this degree and that degree are the same thing, we should divide the leading coefficients. So it should be these numbers. My leading coefficient divided by leading coefficient is 1 divided by 1, which is 1. So I do have a horizontal asymptote. If I have a horizontal asymptote, I don't have a slant. You can't have one or the other. So since you have a horizontal, you don't have a slant asymptote. So now let's graph it. What we know is there's a horizontal line at 1. This graph can never actually become or cross. What happens elsewhere is now the question. So the best way of finding out what happens elsewhere is actually using numbers, plugging in numbers from a table of values in for x, and see what those outputs are to see if it's above the curve, below the curve, and what it's actually doing. Let's look at what it's doing around the x-axis. So I'm going to look at numbers at -2, -1, 0, 1, and 2. So we'll make a table examining those places. So let's see what the output is at -2. So in input -2, I should have -2 squared plus 2 all over -2 squared plus 1. This is 4 plus 2, so it's 6. 4 plus 1 is 5. So at -2, my output's 6 over 5. Practical purposes, because I like decimals when I'm trying to graph, I'm going to call that 1.2. Pretty much what 6 over 5 is. And then we'll figure out the output at -1. So at -1, -1 squared plus 2, or -1 squared plus 1. It's 3 over 2. So at -1, my output's 1.5. That's what 3 over 2 is. At 0, plug in 0, you wind up having 0 plus 2 over 0 plus 1. It's 2 over 1 is 2. So there my output's 2. I think at +1, my output's going to be the same. So at +1, my output's 1.5. At 2, my output's 1.2. You test, you can get the exact same outputs at positive or negatives because you're getting squared here. So let's plot all those. At -2, output's 1.2. So that's 1. 1.2 is about right here. Let's call this 2. So I got something I have a bearing for. So anyway, if this is -1, 1.5 is roughly here. At 0, I get 2. At 1, I get back to 1.5. And at 2, I get to 1.2. So this graph basically is, if I know this is an asymptote, it's going to approach this line forever. Get closer and closer to it forever. Never actually touch it. And on this side, it's going to get closer and closer to it forever. Never actually touch it there. So the graph actually looks like that. So instead of having vertical asymptote, just kind of increases there and then smooths out again to approach that line. And that's a graph for it. So a lot of times when you don't have those linear terms on top and bottom, you have to use test points. I use it around the x-axis or whatever. But if you don't have a vertical asymptote, you have no place to test it. So I generally test the x-axis. But generally, we test around the vertical asymptotes. You didn't have any in this case. But if you're using test points, you should test points to the left and to the right of the vertical asymptotes. All right, I'll get that down as a note. We'll try a couple more of these. All right, so graphing a new function, new example. You actually want to try to graph this function. So right now, I'll let you figure out what the vertical asymptotes are and if there's a horizontal asymptote or not. So pause it, write down the question, and go ahead and tell me what the vertical asymptote would be, or write down what the vertical asymptote would be, and write down what you think the horizontal asymptote would be. And for that matter, if there's a slant asymptote, write it. Go for it. All right, so if you unpause the video, you should have found the vertical asymptote had to be 1. Why? Because that's what makes the denominator 0, 1. Horizontal asymptote, if you notice the degree of the top is 3, the degree of the bottom is 1. The degree of the top is bigger than the degree on the bottom. So because of that, this graph grows forever. So this graph, it gets bigger on top faster than it gets bigger on the bottom. So it never stops growing, meaning you don't have a line that you can get to and never cross or whatever. So it grows forever, so we don't have a horizontal asymptote. Do we have a slant asymptote? Kind of, but not really. It's more of an end behavior asymptote. A slant asymptote is wound up being a linear function. You don't have a slant asymptote. It exists when the degree of the top is exactly 1 larger than the degree of the bottom. Sometimes we have a slant asymptote, and the degree of the top is exactly 1 larger than the degree on the bottom. So if this was squared, it'd be a perfect example of slant asymptote. It isn't. So in this case, we don't have a slant asymptote, we have an end behavior asymptote. Running out of space, so I gotta erase a lot of this. Get down anything you need as a note. I gotta erase some of this stuff. So to find the end behavior asymptote, you need to divide this using synthetic division. So if I divided that, I would take the number that makes the bottom 0, that'd be 1. These coefficients are in the right order, so it'd be 1, -3, 3, and 1. So the 1 comes down, this is 1, -2, 1, 1, and 2. So our new polynomial is 1x squared subtract 2x plus 1 plus your remainder over what you divided by. So our end behavior asymptote is everything except the remainder. So our end behavior asymptote is y equals to x squared subtract 2x plus 1. Meaning our asymptote is actually a quadratic equation. Our asymptote actually should look like a quadratic equation. So when I graph this, so to begin graphing this, we always start off by graphing all of our asymptotes. The first one is our vertical asymptote. So it's 1. So we got a vertical line at 1. Next one is my slant asymptote. To know what this graph looks like, you may know how to graph it or whatever. I like factoring it so I can see the graph. So if I could, I would. This is factorable. This factors be x subtract 1 times x subtract 1 or x subtract 1 squared. If you remember, the equation for a parabola is y equals x subtract k squared plus, actually h squared plus k, where my center are those numbers. So this is really a plus 0 on the end. So I'm sorry, not center, my vertex. So my vertex is at -1, 0. So that's the case, -1, 0 is here. That would be my vertex. And then the graph of this function looks more like this. Actually, I think it's +1, 0. So change that. For the record, +1, 0 will be on the x-axis. So at +1, 0 should be here, and the parabola looks something like this. I'm gonna make it checkered because I can't actually cross it. So that's my asymptote. So those 2 points are my asymptote, and actually get a graph for it, you got to test points to the left and to the right of those asymptotes to figure out where that graph exists at. So I'll choose like 0 and 2 and 3 and maybe -1. So I'm gonna try it over here. 0, 2, 3, -1. At 0, all these go away. You just get 1 over -1. At 2, my output's negative. At 2, my output's +3. At 3, my output's 5. At -1, my output's +3. So I'm gonna plot all those points. You may not feel like that's enough information, but I got enough to know my curve is doing this on this side of it, and asymptoting on both that side and the vertical asymptote on the right side of it. So basically, as this curve goes on forever, it approaches this side of the quadratic forever, and it approaches this quadratic forever. So it's approaching that quadratic. If you zoomed out, you only see, well, that's it. That's how it goes. Good luck.